7. So, right, so 7.7, we talk about conservative, non-conservative forces. So another way, so many different ways you can look at this. We know that the network of any system is going to be net force times the displacement, and displacement in this case was in the vertical axis, so that's really delta y. And we also have determined last time that the total work in a closed system where the conservative force of gravity exists only, where there's only gravity, that's equal to change in kinetic energy, so it's change in potential energy, which serves as our basis for conservation of energy. That's the conservation of energy equation here. So let's just take a look at a perspective there. So we know that the net force is going to be made up of the force of his hand plus the force of gravity. And we know in the whole system, we're going to prove that it's equal to 0. So let's take the net force here and say the net work in the system is going to be the force of the hand and going up or down, it doesn't really matter, plus the force of gravity, delta x, or the displacement, delta x, delta y, doesn't matter what you say there. That's going to be the same. Okay, whether up or down, you're going to go up 2, you're going to come back down 2, so the displacement is the same. We also know here that the forces are equal and opposite, so we can just take a look at this portion of things in terms of the forces here, and we have this is our relationship. So the force of the hand, the guy raising the bar, the block, F of the hand, delta x, is going to be equal and opposite to the force of gravity, or vice versa. It doesn't matter. Remember that when you raise an object into the air, it's going to be equal to something negative. When you raise an object into the air, you're increasing the potential energy of the system, and you're decreasing the kinetic energy of the system. So it's kind of like the same thing here in a different form. And when the object falls down, like in the second case when he was on the other side and the block was coming back down, then we're increasing kinetic energy and we're decreasing potential. So it doesn't matter who has the sign. So just like, you go to Newton's third law, it doesn't matter who's the action and who's the reaction. There's just going to be an action and a reaction. So it's trivial to designate one thing as always action reaction. That's just not sound. I mean, it doesn't matter. So or you can say force of the hand, delta x, fg delta x. It doesn't, it's the same thing. So given that, the displacements are the same. So you can just say the force of the hand is equal and opposite to the force of gravity. You know that by Newton's third law, and you can see that at least intuitively in the demonstration there. So the force of gravity is going to be negative in one case, the force of the hand is positive, or force of the hand is going to be negative, or the work done by the force of the hand will be negative, and the work done by gravity will be positive. So it's just either or. So you can put these guys together. That equals 0. That goes back to Newton's first law. Now you put the displacements on there, which are the same. So there's one way to show that the total work done in a closed path by gravity, that total work done is going to be equal to 0. That basically shows you that gravity is a conservative force. That means that no matter what path you take in a closed path, you're always going to get no change in the energy or no change in the work. The work will be saved. The energy will be saved underneath the conservative force of gravity. But friction always takes energy out of the system. So if you came in hot, if you're an aircraft carrier and you came in at 4 joules of energy and you hit the path and somehow went into a closed path like the block maintained, at the end, you're going to lose all that energy due to friction. And it's going to go into the environment as heat, as sound, into the universe. It's going to dissipate by the second law of thermodynamics. Energy is going to be lost to the system. First law of thermodynamics is the ideal case. It's a perfect system. But again, they're ignoring friction, if you will, ignoring entropy. Second law of thermodynamics is the real thing. You're going to lose some energy, right? Definitely seen when you deal with the physics of engines, different types of engines, diesel engines, car engines, refrigerators, air conditioners. So, the principle of thermodynamics is key. And it loosely borrows from this concept here. Any questions on that? Do we see that in a closed path, the total work in the system will be zero? It doesn't matter what you do, that you're not going to get a change of energy between the same displacement. You can't go up 2 meters and then go down 1. Okay, it has to be the same displacement. And we have the same displacement with the kinetic energy, but as you see, or kinetic friction, the work done by kinetic friction, but you can clearly see, at least know that the work done by kinetic friction is always going to be a negative quantity. You're going to continuously lose and lose and lose until that object comes to rest. Because that's what friction's main goal is, to take energy out enough. So no more energy is taken out, you can't move anywhere. There's no kinetic energy. There's no change in kinetic energy. If there's no change in kinetic energy, you're at rest. How did that happen? Because friction took the work done by friction, or friction took that energy out by the work that it performed on the block. So that's the basic idea. And so then here, you FH, force of the hand, delta X. This is the net work done by these two forces. You could have n number of forces. That's equal to change in kinetic energy, change in potential energy. And we've also shown that that's equal to net work, and the net work in a closed path by conservative force of gravity, that equals 0. 0 is equal to delta KE plus delta PE. There is no change in the amount of energy in the system. It can change different forms, kinetic to potential, but the overall change in the system is 0 in a closed path. Well, under in a closed path when gravity is the only force. And this is our conservation of energy. It brings us all the way back there. So everything is reflexive. You see the patterns in time, or hopefully you're starting to see them now. You close everything off, no change. You leave everything open, we got friction. This is why we stipulate. You see problems that say ignore air resistance, negligible friction, closed path, because this is the ideal situation which approximates to this value. We close everything off from the environment. We get no change in the energy. We leave everything open, which is the real case. Conservation, non-conservation, first law of thermodynamics, second law of thermodynamics. It's all not the same thing, but the principles are the same. And you'll find that you can do a lot of the problems that we did in kinematics very easily just using energy principles. Because with energy, you're not caring about the minutiae in between, like in a free body diagram and have the forces doing this and that. You can find out what energy is going on at the beginning, find out what energy is going on at the end, find stuff. And we're going to do a bunch of examples today. So open everything up, assuming that we're moving. So back in the day, old AP Physics B, Physics 1, we stay conservation. In reality, we must do this as well. I also mentioned that there's another type of potential energy, which is the potential energy of the spring. We derived that a couple of classes ago, and I'm just going to rewrite this equation in terms of the, and include the spring energy term. UK Fn, and let's say that we have the block, the block in the demo is flat on the surface, so Fn is equal to mg. Oh, we got that by now. There's two types of potential energy. There's a gravitational potential energy, and then there's the spring potential energy. So remember the spring going back and forth, right? Always have issues drawing this. So we have this guy, let's say this is x equals 0, it's displaced to the right. So the same amount of displacement here, I'll say right, is going to be the same amount to the left. So delta x to the right is going to be the same as the left, delta xl. So the reason why, just cutting out some middleman there, the reason why the displacement is the same on both sides is because the force of the spring is the same on both sides. Therefore, that force doesn't change, it's conservative. The energy of the system remains the same for spring as well as in the gravitational system. So the force of gravity is conservative and the spring force is conservative. Friction is not. All your so-called conservative terms on the right-hand side, or they group them together, and that's all. And then when there's friction in the system, when it's open, it's going to be equal to the negative work done by friction. So it's either equal to 0 or negative mu k mg delta x, Fn delta x. Newton's laws equal, the net force is either equal to 0 or ma. First and second law of thermodynamics, we have a closed system of work. Everything is nice. We don't have to go to the gas station anymore. Real life, we lose some gas, we lose some energy as the car moves, and we have to go to the gas station because we're losing energy to the outside environment. The work done by the engine is going to not be the same as the energy it took to make the car go. So there's the energy input into the car, which is the gas, and then the engine does its work. And in that process, some is lost to the environment through the gas pipe, the exhaust pipe. So that's where we get our entropy. And that's, we lose. You lose enough, you're not going to be moving anywhere, because friction in real life there has taken a toll, and the car cannot move without the gas. You go to the gas station, fill up, now you can get back out there. And now the hybrids and all that stuff trying to minimize that as much as possible. But that can't, there's still entropy. It's just taking longer. So that's why this term exists there. Questions? Because we saw the spring force is always going to tend towards the middle. It's trying to bring it back to balance. It's trying to bring it back to 0. It's trying to restore it. That's why it's called the restoring force. And the spring force is negative k delta x, negative to, well, indicate its opposite. It's like friction, opposite. And the work done by the spring force, we call either the spring energy or the elastic energy, or we can say the spring potential energy, 1/2 k delta x squared. We did that little integration problem and got to this formula. So that's your formulas here. So V prize, kinetic energy 1/2 mv squared. Change in kinetic energy, You change it, you've performed some work, because a force has displaced an object a particular distance, value, and in the process, you've changed its kinetic energy. You got it moving. E final squared minus VI squared. Then gravitational potential, mgh delta y. Change in gravitational potential is mg final height minus initial height, and so on, right? So it's the same logic. So in these problems that we're going to do, all you really have to do, figure out where the beginning is, figure out where the end, and the beginning and end can be anything. Just like when we're taking the slope of a constant line, if we have a situation of constant velocity, we can take the slope between any 2 points, whether the ends or the 2 points in the middle, we're gonna get the same slope. So same thing with these energy problems. Caveat being, you can find out whatever you need between any 2 points. It's not that all those 2 points will give you the same value, but the principle is the same insofar that you can choose any 2 points to do something, right? So that's what we're going to do.
Mr. Kelly, I have a question. So in the book, sometimes for the potential energy, the initial term is the first, and then there's a one time that final term is the first one. So how do we tell the difference?
I'm not sure what you're asking. I mean, what page are you referring to?
It's on 183. So sometimes final height is the first term, then goes minus
It depends on your
initial.
perspective. It totally depends on perspective. Let me go to 183. What they're trying to illustrate there is that you're going to get the same amount of potential energy uh, no matter what you designate as final and initial. Um, Specifically 183, you're looking at the bottom part.
Yeah, and the page, the left one, there is a one that initial is first. I just want to know, how do we tell the difference? Like, should we always go for final minus initial?
Yeah, final and initial. So in the 182, you're losing potential. So what's going on there is that when you gain potential, this is initial. You increased your height, and this is final. When you lose it, as in negative delta U, as you see there, this is now initial, and this is final. So it depends on your perspective. Don't get caught up in, especially these kind of scenarios. Good question. That it's always final minus initial. It is, but you got to be careful on what is your final. So let's see if we can do some examples in
Does
that.
the kinetic energy work the same way?
Yes,
Okay.
because in this situation, you're going to be increasing potential, like that, while classes ago, increasing gravitational potential and losing this. And one way to kind of like quickly understand that is that once you get to the top, you're not moving anymore. You lost all of that kinetic and you gained all gravitational. Vice versa here. You're going to lose potential, but by the time you hit the ground, it's going to be all speed. You're going to, either smack the ground or parachute. So you're going to be doing this. So the principle is the same. There's no, well, if I switch my potentials, my kinetic is on. No, because it's all like it's perspective. It's the amount doesn't change no matter how you view the situation. Um, it's just that in this situation you're losing because 0 minus something here is going to be negative, but it's going to be equal to all of that. Sure. Does that make sense?
Yes.
Yeah. So definitely, let's see if we can get some examples of that because I had some problems last year where I was out that day, but I gave a bunch of examples of potential energy problems where you're switching your reference points around. But you can prove to yourself you're always going to get the same number. It's just that one's going to be negative, one's going to be positive, and goes back to that the energy doesn't change, just the direction, if you will, or either gaining or losing it. The other book has nice examples of that. I'll try to look about that. PES stand for is spring potential energy. PES is spring. The energy of the spring is never going to change because we have another force that's conservative, the force of the spring. And so again, the force of gravity is the same. Whether you lift something up a certain displacement, 2 meters is going to go down 2 meters. Gravity doesn't go anywhere. So that's also conservative. So they do a bunch of the I hats and J hats. I think we understand that I is X axis, J is Y. I didn't do that here because there are some B people or physics 1 people. And then I'm saving you'll notice that I skipped 7879 for now, but like around late February, March, C people, we're going to come back there and other things to cinch that home. But definitely read ahead. Okay, so that's that. Shoot, let's get to some examples. Okay, so this one was what we started off last time. Out of your text, we have, so for most part, we are complete with 7 for the moment. The C people will come back to 7, 8, 7, 9 in the future. So let's go to some examples. This problem here comes out of chapter 8, number 4. Why don't you guys take some time to do that? I would like you to find, the book says, find the speeds at B and C. I want you to also find it at D, where D is the ground. Okay, so take us a few minutes. Let's let's talk to each other and put your breakout rooms. Yeah. So like I said, okay, let's talk through it. So we have a particle of mass m equals 5 kilograms is released from point A and slides on the frictionless track as shown in figure PA4. Determine the particle speed at points B and C and the net work done by the gravitational force as the particle moves from A to C. There's all kinds of finals and initials, or initials to finals you can pick. So from A to B, you can pick, those are going to be, that's what's going on there. Now, this is it tells you it is at rest or is released. So the implication is at rest here at A, and B is going to still be moving, but it's also going to have a height too. So if this is initial, that's final, at B, what kind of energy do I have there? Do I have 1? Do I have 2? What's going on there? Do I have kinetic energy at B, potential, or neither?
Potential.
I do have potential. Do I have kinetic or no?
No kinetic, right? Because it would fly off.
No, we have both. Because from A to D, let's say, is going to be a continual conversion of potential into kinetic at the ground. But in the meantime, we're going to have different, and Emmanuel, you answered this last time. But in the meantime, we're gradually losing potential, gaining kinetic, because as it goes from this maximum height, which is all potential, all gravitational potential, and at the ground, it's going to be all kinetic. In the middle, it's going to, you're going to have both. So in the middle of things, you're going to have you're going to be losing one form and gaining another. But at the ground, you're going to be one or the other. Yeah, I will be really sorry about that. Does that make sense? I mean, can you get with that? I mean, there's all kinds of ways we can dissect this problem. I wish I was in class and I could just show this, you know, this thing is going to be moving and it's got a height. So to convince you that there is kinetic and potential, we know there's potential because, hey, there's heights, but maybe that's not so convincing that it's kinetic. Or else if it was not kinetic, the guy would just, you know, come here and stop. There's a reason why.
So if B was as high as A, at B there would be no kinetic.
I'm sorry, ask that again.
So if B was as high as A, at B there would be no kinetic energy.
Exactly. There would be no kinetic at A. So at A, the object's at rest. So let's just space is 0. Therefore, at A, all potential. Okay. At B, we are. Is there? Let me ask this: Is there a reason why you're not convinced that B is moving? You can see the potential. With why don't you see that it's kinetic as well? Because we need to explore that. Let's say you have a ball in the air. I'm holding a ball, and I let it go. Is there any point in the fall that the ball stops before it hits the ground?
Not really.
What do you mean, not really?
No, there's not.
It either is or no. No, it's gonna hit the table. Let's say the table is like 2 meters under my hand. It's gonna continue to fall down. Now, if you were to take a snapshot of each second of the fall, let's say it takes 5 seconds, you're gonna see that it has height at each of those seconds before it hits, but it's actually still moving through the air at the same time it has those heights. So not only is there potential energy at B, there's also kinetic because it's continuing to move until it hits the ground. Once it hits the ground, that's it. There's no more potential, but it's all been converted into kinetic energy. So the same thing goes. So this path, notwithstanding, let's just take the path on this. Let's just take this guy here, because this is what's really going on. I'm dropping a ball from A all the way down to D. This path is not important. So I know that here is all potential. Oops. And then here at D, it's all kinetic. In the middle, there's different stages of each. I'm slowly converting my potential into kinetic until I get to the end where it's all kinetic. And likewise, if I raise the ball up into the air, I'm going to slowly lose that kinetic and it's going to become potential. But in the middle here, it's both. Different amounts of both. Yeah, it's kinetic energy. It's still going to be moving here and it's got a height. So it's both kinetic and potential. Once it hits the ground, all kinetic. At the top, all potential. In the middle, different amounts of both. Got it? Rule of thumb. So again, if I just drop this ball down, potential to kinetic. In the middle, I have different amounts of both. And we're about to do the solution now. But conceptually, that needs to be understood, because I don't want to leave you on this one and then get to another one, like we have a mass on a ramp. It's, yeah, we're going to need to understand that logic there. Okay, so let's just dissect this out. So we have A to B. So A is all potential. Are we convinced here that it's all potential? It starts from rest. Is that iffy or still confusing on that? You guys good on that? Let's see. You must always keep the basic definitions in mind. That potential energy, if the object's not moving, then logical conclusion is that the energy at the beginning, if it's got a height, it's going to be potential, because potential is a function of that. Now it could be moving too, but we at least know that at A it has this. But the problem infers, you can infer that it's at rest because it is released from, Sometimes it's not going to be as cookie cutter and say the object's at rest. So the initial situation, in the initial case at A, initial point, all the energy is potential. And then at final, the other point in question, which is B, the easiest problem would be, okay, it hits the ground and okay, it's all going to be kinetic, but it's still in the air. So at B, it has potential and kinetic. And now what we need to do is find the speed at B. And then I'll let you guys go and solve some other things there. So you got MGHA, MGHB plus 1/2 MVV squared, and this is the guy in question. Yeah, one thing at a time. Maybe with the solution here, you will see what D is all about. But yes, of course. Don't fret, guys. I mean, you take things one step at a time, but you are silent because you have a question and you don't know how to ask it. You cannot do that. You have to ask. I don't care what it is. Must ask. The masses cancel out on both sides. Same everywhere. And we're trying to find B. So we have GHA, subtract this guy, minus GHB equals 1/2 BB squared. Masses go away when they're subtracted these terms, and so I can factor out my G over here. I'll multiply both sides by 2, like fractions, add to the U. Okay, so 2GHA minus GHB, BB squared. It's like kinematics equation, don't it, huh? So I can just take out my 2G HA minus HB equals BB squared, then square root of 2G HA minus HB. And my numbers. And the height at A is 5, the height at B is 3.2, and that's my speed at B. All right, so what do you get for that? And calculate.
So it's basically the same equation, the kinematic equation. We just found it with the energies.
Yeah, but again, I don't. Short answer, yes. But energy, you'll find, is going to be a lot easier to do instead of just trying to figure out which kinematics equation I want to use, because once you identify what's going on at an initial point and at any final point you choose, life becomes easier. Tell me where you need to scroll. Yeah, maybe it's the demo is lagging me for some reason. I'll see about that. The 2mg equations, yeah, that's serious lag. Right here, the potential energy is mass times gravity times HA. And another question, and also we ignore the curves and the masses. Absolutely. That's the math is telling you that. And then even you can infer that from other principles, well, whatever. But yes, the masses is not important. So if I, the last time, so the more we ask the same thing, yeah, keep on doing that. The mass, I put a ball at 5 meters there, I put a truck at 5 meters there and release either one, it's going to have the same speed at the bottom. Because it's all about what's going on between the start and the finish, whatever you designate as finish. Because the finish for now is B, the other finish could be C, or you could go from B to C, or B to D, C to D. It doesn't really matter. But of course, the entire course would be from A all the way to D. That is the full picture of the example I was talking about earlier. I have my ball in the air and I'm dropping it. D is the table, but in the middle, it is still in the air and it's moving. That's why it has both energies at B and at C. Energy is saved because we're closing it from the environment. There's no friction terms here. Okay, so 5 times minus 3.2. So about 5.9 at B. Meters per second. Those numbers check themselves. And you do likewise for C. Now, a couple of options for C. You could take the energy at B and go to C, or you can go from A to C. It doesn't matter. you know that when you're still in the air and you haven't gotten to the end, when you got to the end of your journey, it's all kinetic energy, but in the middle, it's both. So you can go from A to C, potential energy here, potential and kinetic there, potential and kinetic here, potential and kinetic there, potential and kinetic here, kinetic there, right? All right, so let's answer the rest of these. Let's take about 10 minutes to do finding the speed at C and at D, and then do part B, which is finding the total work in the system. From A to C, though, from A to C. Okay, so breakout rooms. Okay, so we got part B and C. So again, we can go from A to C, or B to C. B to C is a little complicated because it's both. So we're gonna go, we can choose anything. So my initial A and my final is C. So with energy, it's really using the full power of displacement. So I can have a loop to loop and curve, go all the way, I can get it a messier curve. I understand that this is the most important thing. That's all that's going on. This here's it's junk. No. Biblical story, the Hebrews coming from Egypt, they could have gone this way, but they went this way. They still got there. Went through too much. So at A, it's all potential. And then at C, it's potential and kinetic. It's the same logic as before. Yeah, or like I said, you could choose my initial is B equals final at C, but at B I have both, and same here. And I get my kinetic after finding out what the speed is at B, which I did in part A, and then multiply that by the potential energy at B. Then I can find my velocity at C. So I have my MGH here, I have my speed here, or I'm trying to find my speed there. But as you can see, this is better. It's not as messy. So choose the top. MGHA equals MGHC plus 1/2 MVC squared. Masses cancel out. And so I'm just going to basically have the same equation up top. I'm going to cut out all of this. I get the same equation here. And so that leaves me with velocity at C is the square root of 2G HA minus HC. So I get 5 minus 2, which is 3, and the square root of 58.8, 7.67. And the signs all come out to be what it should be because it's increasing speed. So it's going to be positive. Whereas if I was raising it back up, this would be I'm going to be losing this amount as I get all the way back up to A. No. And then, so the net work in the system, we have a couple of options. Yeah, so I'll do that. So we could do this, or we could do this. So, because it's both equal to both of those. So the net work done by gravitational force is going to be a negative change in potential energy. So the work done by gravity, as the mass comes down, displacement's down, force of gravity is down. So the work done by gravity is positive, but I'm losing potential energy. And so negative mg A to C. So I'm going from 5 to 2, just 3, G3, and then some negative 5 kilograms, and that gives me negative 147 joules. So that's how much work is being done by gravity. So again, you get to see what we stated as true, prove that was true, that the work done by gravity is going to be a decrease in potential energy. Because now that the force of gravity is pulling on the mass coming down, anything is going to the curves, it's pulling it down, I am losing potential in this amount. And if I raise it back up, I'm going to gain the same amount back. Nothing changes, just the form. And this will be the change in kinetic energy. It's going to be 147 joules gained in kinetic, which is equal to this, right? Negative 147 joules of potential loss is going to be exactly equal to that amount gained. No change in the work. Gravity is a conservative force. And then D, yeah, I was saying find the speed at D. Right, yeah. So that's the easiest case because we're going from start to finish. I'm dropping the ball, hitting the table. Potential energy at A equal to kinetic energy at D. Because at D, there's no height. At A, there is height, but no speed. D, no height, but speed. So mg A, 1/2 m squared square root of 2 HA, where the initial at A is 0, kinematics equation, a VF squared equation. It's just like so beautiful or rhythmic that you use the energy equations that you come back to the kinematics. Is why? Because gravity is just this, it's going to do the same stuff. So HA, all right, yeah, 5. And this will do it at this point. And well, anybody sticking back for skills tests, do that. So that's like 9.9 meters per second from start to finish. And notice that it went from 5.94, 7.67, and 9.9 is at full speed. It's fully converted. Okay, so I'll be back in 10 minutes the office hour link. Any last question on this? Yeah. So anybody coming back for skills test? See you in 10 minutes.